Okay, today we're going to be moving on to section 4.5. We were doing 4.4 the other day. We were taking a few notes. We had 3 postulates up till this point that we've been using to prove that triangles are equal, right? We've used SSS, 3 sides. We've had SAS, which is side, angle, side. And we've had ASA, which is angle, side, angle. Those are the 3 postulates we've had up till this point. Today, we're still dealing with this idea of like, are triangles equal to each other, right? But we have some new properties, and they're actually really specific properties for special types of triangles. So the 3 that we've had up till this point work with any type of triangle. They could be right, they could be equilateral, they could be isosceles, they could be obtuse, it didn't matter. But today, some of the ones we're going to learn today are definitely not. So here's kind of the outline of the goals I want to cover today. I want to do theorem 4.5. That's the first one I want to make sure of. It's one of the last acronyms we're going to have for the 3-letter systems. Okay, so like we had SAS and ASA, right? This is the last one. We're actually going to talk about the proof of it, which is really short. I believe it's 3 lines, 3-line proof, something like that. So we'll kind of look at it. That one has its own acronym, so we're going to add that to the list of the 3 that we have. Even though it's a theorem, it's not a postulate, we're going to do the proof and we'll use it from now on. It just makes certain problems easier if you know this one. It is not necessary that we have this. It does make some pictures easier, which we'll see later. Some of the later ones we'll use it. Some of the vocab terms today we're going to look at will be on the special cases. We're going to look at certain specific type of triangles. So there's a slide where we'll throw in some vocab words at you. And then we have a couple of theorems. I don't think we're going to get to all of them today. We're going to just do a few. But we have a few theorems today, 4.6 to 4.9. And all these theorems are based on very specific types of triangles and how do you know that the pictures are equal. So that's what we're going to look at today. Now there's a few that we're going to prove. We're not going to prove the last one, which I know is really weird, even though it is a theorem. We need to wait to prove that one until a later date. We actually need some vocab words in the later sections. So this one, we're going to take it for granted, 4.9, until we can prove it later. I think they went about out of order with that one, but I can understand why they're doing it. Because they're mixing with all the others. But okay, but this is kind of our outline today. Now we do have homework due, so keep that in mind. That was a page 268, 278. That was the stuff we got Friday. That particular homework, I think one of them was a graph, so you needed one graph if you didn't get one. I have some up here. And then 3 of them were proofs. One was a flow chart where you don't have to give me any reasons. You just had to look at the instructions, what they wanted. But yeah, they were using the old one, so that was due today. So keep that in mind. Okay. All right. 4.5. Let's start right in off the bat. There's some vocab words we're going to get later, but for this one, this is basically almost exactly like to the other theorems we've had. So here's the words. This is what it says: 2 angles and a non-included side. So this one uses the word non-included. Now the word included that we've had previously, last week, we said the word included meant in between. So now we're not in between the 2 sides, or the 2 angles, I mean. So we have 2 angles and the non-included side. One triangle are congruent to the corresponding parts of another, then the triangles are equal. I'll give you the picture and then we'll get to the naming system. We'll actually talk about why this one is proved, all that good stuff. So I'll let you write it down here. Alright, now we are going to prove this one. It is a theorem, so we do have to prove it. It's going to use one of the previous postulates we've had. We've had the 3 postulates: SSS, SAS, ASA, right? We're going to use one of those to prove this one. Now, after we prove it, then you can use the acronym that this one provides you. It's the 4th acronym that we needed. I said there was going to be one extra one eventually, other than the main 3. But anyways, on this particular picture, you can see the setup. They have two angles given in both pictures, and they have a wall that is not in between them. It didn't matter which wall it was, but it is not in between. It's not included. So if you're looking at like the acronym system, what we have here, this is the acronym system that we have. It's spelling the wrong acronym, right? This one, if you go clockwise or counterclockwise, this is the acronym that it's spelling, right? AAS, where the side is not in between them. We're just doing a few notes here. So the idea is that we need to prove that the two triangles are equal to each other, but it's not the right acronym. So to prove it, you have to start with what they provide you. So if we're doing a full-on proof, which I'm not going to do here, but if we're doing a full-on proof, you list all the equal parts. So they gave me, angle B is equal to angle E. They gave me angle C is equal to F, and this wall, which we'll call AC, is equal to DF. So they gave me the certain walls are equal. Okay, and that's all line 1. You write all the givens. Line 2. Now this is the weird part. Because I do need to get to 3 markers that spell the right acronyms. The acronyms we have up till this point, the only 3 we have are these 3 that we can use. We can't use the new one, not until later. Okay, these are the 3 that we have. Okay, so when you look at the spelling of the acronym, it doesn't spell the right one. It's close to this one, but it's not. So in the second line of the proof, if you're actually doing a full-on proof, you'd actually list that angle A, this third angle, is equal to this angle over here, this third angle. And we had a theorem based on this. So this is something we did before the semester test, was we talked about, it was theorem 4.3. Theorem 4.3, you don't remember, theorem 4.3, oh, there we go, 4.3, it was on page 257. It was called the third angle theorem. The third angle theorem, and what it stated was that when you have pictures of triangles where 2 angles are shared in both pictures, then the third angles are also shared. They have to be, because what do triangles have to add up to be for angles? 180. So if you know that 2 of the angles are the same, the third angles are forced to be the same because all triangles have to add up to be 180 no matter what. So it is forcing the third angles to be the same. And now you can definitely tell by the markers what acronym proves it. So the third line of the proof is that you can prove that the 2 triangles are equal because it spells one of the acronyms that we previously had. It spells ASA, which is this one. This is the reason why this theorem works. This theorem, 4.5. Now, a lot of people look at this and go, well, Ward, why do we need this acronym? We proved it using a previous one, but it makes it easier. From now on, you don't need to show the third angle. If you have this set up on the picture, you can immediately jump into the point where you know that the triangles are equal because of the new acronym. So the acronym we're going to use is AAS. So that's one of the 4th ones we're going to add to the list now. So we can add this to the bottom of the list. That when you have a picture of triangles that are equal, it's because of one of these 4 acronyms. But this is the new one. I know it's kind of a controversial one because it uses one of the previous ones to prove it, but it is still one of the 3-letter acronyms. It is one of the only remaining ones that we need. Okay, there is no other 3-letter acronyms anymore. That's the last one. But it is controversial because it requires one of the previous ones. Okay. But again, it used a previous theorem that we had before the semester test, which is called the third angle theorem. Theorem 4.3. Okay, questions on the new theorem here? Okay, it was just one of those, I wish I would have got to it last week, but we needed time to work on the homework, and it didn't have the same wording as the other ones, and I didn't want to do any proofs of it yet. We're going to get to this. We actually need this one to get to those later ones that we're going to have, the special cases, I should say, to prove that certain triangles are equal. Okay, let's move on. But again, we have the 3-letter acronym systems now, where there's up to four different ones you can use. But today, what we're going to be really focusing on in this later part is special types of triangles. What I mean by, because these other ones used any type, we're going to be focused on just right triangles today. That's it. That's all we're going to focus on the rest of the day. What is a right triangle?
90 degrees.
Yeah, it has one angle that's 90, right? These are some of the words we need to know. We need to know what a leg is, what a hypotenuse is on a right triangle. Those are special keywords. Let me give you the picture here that labels it. A leg of a right triangle, as you can tell, there's two of them. The legs have to touch the 90-degree marker. I don't care if they're the same length, if one's longer than the other, as you can tell from my picture. The two legs are the ones that touch the 90-degree marker, though. The biggest wall of a right triangle is always called the hypotenuse. The hypotenuse is always the wall that is across from the 90. It's across the picture. It does not touch the 90 degree. Now the reason why that's called the hypotenuse, that would be a Greek term for it. But again, it's across from the 90-degree marker. It is the biggest wall because it's across from the biggest angle. We're actually going to use this picture quite a bit in the later sections, especially when we get, I think it's chapter 9. It's chapter 9 or chapter 5. I don't remember which chapter number it is. We'll start dealing with the trig functions. Certain buttons on your calculator that help you find length of walls, Pythagorean theorem, that type of thing. But they require that you know these words. Know what the legs are, what the hypotenuse is, because the formula will ask you to plug certain numbers into certain spots. All right, questions about right triangles and the vocab? Okay. Again, we've had a few properties about right triangles up to this point. One of the properties we've had on a right triangle is that the two remaining angles in here, the two remaining ones, are acute and they're complementary. We have that where these two have to add up to be 90. That was in the previous chapter. It was in the previous sections. I think it was in section 4.3 even. The one we had before our semester test. Because again, it's dealing with triangles and what they add up to. Okay. Now I know this seems a little weird. We're going to use some of these words today to go to these next few theorems, but that's so when they start talking about right triangles, these are the vocab words they want you to have in like the back of your head so they know what you're talking about. Okay. All right. Classifications of right triangles here. Right triangles can only be two specific types, other than talking about the angles themselves, right? The angle, if we're going to classify the triangle by its angle, we call it a right triangle. But the other three names you can call it by its side lengths, right? Other than its angles. A right triangle cannot be equilateral. It cannot be. One of the properties we've had about equilaterals is that the angles had to be acute. On a right triangle, one of the angles is right, so it can't be equilateral. So the only two types it could be scalene, like this picture, where all three walls are different. And it could be isosceles. Two walls could match, and those would have to be the legs. That would be this situation where the legs are exactly the same size, even though it is still a right triangle. It could be one of these two types. So keep that in mind. It could be scalene, where all three walls are different, or it could be isosceles, where two walls are the same. Now, we're going to see, I think we're going to do isosceles maybe later this week. It will be probably Wednesday we'll start messing with isosceles. But I want to make sure that we understand the vocab terms that are involved. Okay, let's get to one of our theorems, our new theorem today, 4.6. We're going to try to prove that certain triangles are equal here. So here's the setup. It's got the same wording as kind of the other ones, but definitely not a three-letter acronym system. So if the legs of one right triangle, just the legs, the two legs, if the legs are congruent to the legs of another right triangle, then the two triangles have to be equal to each other. But again, this is very specific. They're talking about just right triangles, where you just are given the legs. And we have to prove that the triangles are equal. I'll give you the picture. So we have right triangles only, two of them. And we're just given the legs. So just two legs are matching. Now, if we go back to that last picture we were just showing a little bit ago, like, what is a leg? What do the legs have to touch in a right triangle?
90-degree marker.
Yeah, the 90-degree markers. So we're given this, okay? So we're given that, you know, on my pictures here, we're given that the two legs are matching on the two pictures. So maybe the shorter wall is equal to this shorter wall, the medium wall is equal to that medium wall, and like you guys said, they have to touch the 90-degree marker. Well, why would these triangles be equal to each other? What acronym does it spell? Yeah, SAS, right? Side, angle, side. It does spell it right away. Side, angle, side. That's why this works. But again, it's a very specific type. All it was given, though, was the two walls. But it still worked. Because you knew that it had to touch the 90-degree marker because of the way the vocab work. And so it does spell the right acronym, SAS. Now, again, the legs are the two walls that touch the 90 degrees. So that's what they're giving me. They're just the two legs. Now, the name of this one is going to come up later, but doesn't use a three-letter acronym system because I know it spells SAS. But again, for a right triangle, the reason why we proved this is because of SAS, right? That was the reason why we proved it, because of the acronyms that they spell. Because remember, any side mark you put an S, any angle you put an A, any side mark you put an S, and that was the reason why this thing worked. But the acronym that we use, other than the three-letter system, this is the name we're going to call it. We're going to call it the leg-leg theorem, or leg-leg congruence theorem. But again, they only work, these 4, 6 to 4, 9 only work because they're right triangles. Now, abbreviating this, and other than calling it leg-leg congruence, we call it the LL theorem. The LL theorem. LL. The two legs match, then the right triangles are equal. And they had to be a right triangle for that to work. If it's any other type other than right, this doesn't work anymore. So LL theorem. But again, it does spell the right acronym. We already know that by looking at the picture. Okay, questions about that particular theorem? Okay, let's get to the next one. Again, these are all short abbreviations. They have quick proofs. Now, why do they work? They use one of the 4 words, one of the 4 acronyms that we've had up to this point. Okay? All right, so theorem 4.7, I should say. It does have a name, which has, you know, a very quick, you know, abbreviation to it. But again, if the hypotenuse and angle of one right triangle is equal to the hypotenuse and corresponding angle of another right triangle, then the triangles are equal. So I'll give you a little bit of time to write that down. So now they're giving us a hypotenuse and an angle. Now, what specific type of triangle does this have to be again?
Right.
Has to be a right for this to work. Now, the 4 other letter acronym systems that we did, you know, SSS, SAS, ASA, or AAS, those didn't require a specific type. These 4 do. They have to be a right triangle for these next 4 to work. That's why we've been doing these. So we had LL. This one has another name, but again, let me give you the picture. So they're giving me the hypotenuse and an angle. It didn't matter which angle, it had to be one of the acute ones of the triangles. So here we go. So there are 2 right triangles, as you can tell. The hypotenuses are marked. The hypotenuse is the big wall, so we had to have that marked. And they gave me one of the small angles, and it didn't matter which one, but one of the smaller angles was matched. Now, if we're thinking about the 3-letter acronym system, okay, which one of these 4 proves that? Which acronym does it spell? Oh. AAS, yeah, because the side is not in between the 2 walls, or the 2 angles, I mean. The side is not in between them. So as you wrap your way around, it is spelling AAS. because the side is not in between them. That's why it's not ASA. It's a common mistake, but it's AAS, right? So that would be the reason why this one actually works. But now the name of this theorem, since they're giving me a hypotenuse and an angle, that's actually the name of it. Hypotenuse angle theorem, or congruence. But if you want to abbreviate, you can call it the HA theorem. Called the HA theorem. But again, the reason why is because the side is not included. It's not in between the two angles. So it's AAS. All right. Any questions so far on the three that we've had, or the two, I guess, 4, 6, and 4, 7? Okay, HA we abbreviate because again, hypotenuse and angle. Good. Nelson, whenever you're ready. Good. Okay, all right, let's go to the next one, 4-8. So same exact idea again. So now we're giving a leg and acute angle of one right triangle or congruent to the corresponding leg and acute angle of another right triangle. Then the triangles are equal. So now we're given a leg and an angle. So what do you think they call this one? What do you think the name is called? Yeah, it's called the LA theorem, or LA congruence, leg angle congruence. So instead of leg or hypotenuse angle, now it's called leg angle. I'll give you the picture here. So we're given a leg and one of the angles. Now this one can be controversial, the way that it's presented to you. But again, we're just given an angle and a side, like a leg. An angle and a leg. Not the hypotenuse, but an angle and a leg. Now it didn't tell me which angle, other than the right one. It had to be one of the acute. So this one, I don't agree with the way that the book presented this picture. It's kind of controversial because it makes it look like this is the only way the picture could be presented to you. So after we're done with this one, I'm going to get rid of the picture and show you the other one that could have been here. Because again, they were just giving you a leg and one of the angles. So that's why I don't like the way that this is the picture that your book had. I don't like the way that they presented it. Okay, now by looking at this picture and you're thinking about, the 3-letter acronym system, why this one has to work, which one of the 4 does it have to be?
ASA.
Yeah, ASA, right? Because the side is in between them. That's the way it makes the picture look. It looks like it should be ASA. The problem with this is that didn't have to be the only picture that they provided you. That's why I don't like this one. Because instead of this picture, they could have gave me this one. Where they gave me, the right triangle, so they're right. They gave me the wall, but what if they gave me that angle? Okay? Because it didn't say that the leg had to be in between the angle and the right angle. It just said they gave me an angle, they gave me a leg. Do you agree? I gave you an angle and a leg. An acute angle, anyway. Okay? Well, if you look at the 4-letter or the 3-letter acronym system, and you look at that one, now it's the Aas theorem. That's the reason why it works. Because of angle, angle, side. Angle, angle, side. But again, the only reason why they provided you that one picture earlier, the one I got rid of here a little bit ago, is because of the reason for this one in the first place. Like the proof we did earlier, like the first slide we did, how I proved that this is one of the acronym systems you could use, because you could use the third angle theorem, placing this one down here. And now you do spell the right acronym that they showed you earlier, ASA. I just don't like the way that they showed you that it had to be that one picture in the beginning, because obviously I'm showing you a completely different one here. But I understand like possibly their logic behind it. I just didn't like it. It assumes too much. But again, the name of this one we already said it. It's called the LA theorem, or leg congruence theorem. LA theorem. Good, everyone's got it? Okay, now the next one. We're not going to prove the next one, right? All these others, I've been proving it, blah, 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 blah. The next one, we're not going to prove it until later, like why it works. Now, I'm going to pre-warn you. When you first look at the picture, it definitely doesn't spell one of the right acronyms. It's possibly the one that everyone has been waiting for. They've been waiting, I'm giving you the 3-letter acronym systems. And everyone is always waiting for one specific one, and I'm going to show you why. So, here we go. For now. So, a hypotenuse and a leg of one right triangle are congruent to the corresponding parts of another right triangle, then the triangles are equal. It's the one that everyone's always waiting for. I'll explain why once you see the picture and have a good chuckle about it.
Yeah.
Hypotenuse and the leg. So let me give you the picture, and then we'll talk about the acronym system. So you're given the hypotenuse, and you're given the leg. Now, as you guys are, I know you're still writing and stuff, because it is kind of long. Is the angle in between the two legs? No, it's not. It's not what they call included. So it's not. So if we're thinking about the angle is not in between the two side markers, right? These are side markers. The angle is not in between them, so it's not the SAS theorem. It's not. It's not that one. The angle is not in between. In fact, I'm going to write it backwards. This is what we have. And yes, I wrote it backwards on purpose. We're not talking about donkeys, okay? It is the one that everyone waits for. They're like, yeah, it's going to spell the right acronym. It doesn't work, okay? We're not going to prove this one yet. We have to wait till we get to the next theorem. I think it's like theorem 4.7, I think. Or not 4.7, 4.10. 4.10 is the theorem that will lead us to why this one has to work. Why it has to work for a right triangle, okay? But now the name of this particular theorem, as you can tell by they gave me a hypotenuse leg, we call it the HL theorem, or hypotenuse leg congruence. But the reason right now is not apparent, and I can't prove it to you because we haven't got to a later theorem that we need, which I know is a little bit underwhelming. Like, I want to show you why it works, but you don't have all the tools necessary yet. I can just do it for you right now. It's a very long proof. I think it's like 7-8 lines long, like full-on proof. But one of the steps is controversial because you haven't seen the proof yet for that particular theorem. You haven't got the theorem yet that would prove why this one works. But it does work. You're just going to take my word for it until we get to the later section. It's the next section coming up. It's section 4.46. Okay, that's it for today. We're done. You have about 7-8 minutes here left. You can kind of relax. Now, if you do need to work on your homework, page 268, 278, this would be a good time to finish it up, turn it in. We'll like those today. I know we had snow days, so I'll take it easy on you today. I want it at some point today if you can, not just right now. Okay.